Elementary steps. So let's say you're given a problem like this. Essentially, I've given you an entire reaction scheme, right? And you have no reason to have any idea what this reaction is at this point. Okay, all I would want you to be able to do is, one, track where the electrons are going, okay, to figure out how to draw in curved arrows, and two, label the types of mechanistic steps. All right, so I'll give you a second to copy it down. So when you're doing this, don't let the length of it or the complexity of it throw you off. Just kind of like you did with resonance, treat it as one step at a time, just very carefully. All right, and essentially look at what's going on. I should probably add my Cl- here. Look at what's going on in each step individually. Okay, so in this first step, you're somehow adding a proton to the oxygen. Okay, well, never start your arrow at the proton because it doesn't have any electrons to give. All right, and when you're doing this, if you're having trouble thinking about where things go, draw in lone pairs, and that'll help you identify nucleophilic sites where you can move electrons. So here, I can take the 2 electrons on that oxygen, draw an arrow to the hydrogen. That's going to form a bond with the hydrogen, which is what I want in the product. Okay, but this is just an acid-base reaction. Remember that the hydrogen can't have 2 bonds, so at the same time, draw an arrow from that bond, just saying those electrons are leaving and going on to the chlorine. All right, so that gives us the products in the first step of the reaction. All right, then this you want to identify as you're taking a proton, transferring it from the chlorine to the oxygen. This is a proton transfer. Okay, then we can do the second step. Now look at this individually and try to figure out how we can start with this positively charged species here and add water to that and get this product. Okay, so water, you have the lone pairs on the oxygen that can act as a nucleophile. And if you look in the product, what you're essentially doing is forming this new bond between the water and the carbon. Okay, so to do that, we're going to use the electrons on this oxygen. And draw an arrow to that carbon. Okay, that'll make the bond, but this double bond can't stay because that would give that carbon 5 bonds. So at the same time, just move the pi bond up onto the oxygen. And doing that makes the oxygen happy because now it has its 2 bonds that it wants. Okay, so we get the water attached. This step here, you're taking a nucleophilic species, adding or attacking an electrophilic species, so that's a nucleophilic attack. All right, then the final step of the reaction, we have this species here with the OH2+. We're reacting that with more water, and all that's happening is you're taking a proton off of that oxygen. Okay, so to do that, we're going to use water and the lone pair on water. So put your pencil down at that lone pair. Draw an arrow to this proton. And then another arrow leaving the proton, again, because it can't have 2 bonds. All right, so this is just another acid-base reaction where you're transferring the proton from this oxygen onto water's oxygen. So that's where we get from the water and that proton, that gives us the H3O+. And then you're left with the final product. Right? And this one you would identify as another proton transfer. All right, so this is something, as we go through reactions, you're going to want to get really, really good at. But we're going to talk about using these curved arrows in conjunction with every reaction that we do. All right, so there may be a couple questions, not a significant number of questions on this stuff, but a couple just asking you for a step to draw in the curved arrows to show how electrons flow. The other type of thing you could potentially be asked to do let's just say I gave you some starting material or some reactive intermediate, and I drew in the curved arrow for you. Okay, then you want to figure out what happens. Okay, so that's just about tracking where the electrons are going. And here, I'm breaking that bond. So this specific step here we call loss of a leaving group. Okay, and what you're losing is water. So you get that as a product. But then you're breaking the bond to that carbon, so you're taking electrons away from the carbon. That'll end up being a carbocation. So that would be the two products from that mechanistic step. All right, so here's a couple of carbocations you want to look at for potential rearrangement. And so start by identifying the carbon where you have your carbocation, and then look at the adjacent carbons or the neighbor carbons. So in this first one, you have neighbors on the left or the right. Okay, and then look and see if either of the neighbors have hydrogens. Well, the one on the left does have a hydrogen. So if you can do a rearrangement to get something more stable through a hydride shift, that's best. So now just kind of think in your mind, okay, so I start here, this carbocation has two carbons bonded to that carbon, meaning it's secondary. Right, so if you have a side that has a hydrogen, think about whether shifting that hydrogen will make it more stable. Right, in this case, if we shift the hydrogen over, we get the plus on a carbon attached to three other carbons, that'll be tertiary. So that is our best choice. So because we can gain something by doing this hydride shift, don't even worry about the side where there's carbon groups. So I'm going to draw an arrow basically showing the two electrons in the carbon-hydrogen bond jumping over to the positive carbon. If you want to draw that hydrogen in, you certainly can, or you could just leave it implied, as we typically do. All right, but by taking the electrons out of there, you get the positive charge on the neighbor carbon, and that is now tertiary. So it's more stable, so that's what will happen. All right, now this one down here, first if you just identify the carbocation, that one is on a carbon bonded to just one carbon, so that's primary. All right, find its neighboring carbons, and this carbon only has one neighbor right here. Okay, and here there's no hydrogen to shift to make that more stable through a hydride shift. So what we'll do here is a methyl shift. All right, if it helps you to kind of keep it clear what you're doing and you want to draw in the CH3s, you can certainly do that. So I'm going to take one of those methyls with the 2 electrons in that bond and shift that over and attach it to the carbon with the positive. So we get that new bond. And then this carbon that we started with where I put the blue dot. We took those electrons out of it. So that'll have the positive charge now. And by doing that, you go from a primary to a more stable tertiary carbocation. All right, I'll show you one last one quickly because this one tripped a lot of people up on an exam. Something like this. And if you look at that and look at the neighboring carbons, we have a secondary cation. And just on first glance, if we shift it to the right, it'll be primary. If we shift it to the left, it'll be secondary. So, you might be tempted just to say, well, that's not going to rearrange. And typically that would be the case. But what you have to recognize is this isn't just a secondary carbon. It's next to this double bond, which means it's called allylic. Okay, so let's look at what happens if you do the shift. Let's take one of the hydrogens and draw that in. Shift it over. All right, now you get this allylic carbocation. And that's more stable because of resonance. So anything you can do there to make the carbocation more stable will cause a shift. All right, so this one, remember you can move that pi bond toward the positive charge. And draw a resonance structure. All right. Yeah.
If you have that question, say on the exam, would you expect us to draw the resonance structure, or
No.
it's resonance stabilized? That's it.
Yeah, I mean, if you were asked to explain why, even just saying it's resonance stabilized, that would be sufficient. Yeah, so like converting a 2D structure into a Fisher projection, or?
To a line and then a line to a Fisher.
Okay. Switch the top and bottom groups. These two have different connectivity, so this one is a constitutional isomer of that one. But it's a different molecule, but it's still a valid Fisher projection.
If you like how you drew that on the bottom and you switch the BRCl with the OHH, is that identical? Just turn.
Yeah, so then if I drew it, so we put the Br and the Cl on the top. And then the H and the OH on the bottom. Okay, so by doing that, this ends up being the enantiomer of this one. All right, and the way to see that is, like if you just rotate this 180 degrees to put the COOH back at the top. All right, that rotation will rotate this OH to the top left. And after doing that rotation, it'll put that Cl to the bottom left. And these two structures are non-superimposable mirror images. Does that make sense? Okay. All right, so let's say you want to put this Fisher into just a 3D zigzag type structure. The easiest way to do it is build a model and convert it like that. But if you don't have a model to use, what I would actually start with doing is just to help orient yourself with the directionality of the groups. Okay, you need to know that the vertical groups are pointed away from you. So let's make those dashes. And the horizontal groups are pointed out towards you, so let's turn those into wedges. Okay, and this vertical chain, it kind of depends what side, because all of those groups are wrapped around kind of going to the back. So depending on what your viewpoint is to convert it, you can kind of view it from the left side or the right side. And either would be valid as long as you correctly work from that. But what I would just do is, think about having these, you have a chain of 1, 2, 3, 4 atoms. Okay, so draw a semicircular or semicyclic species with 4 atoms. Okay, it would just be like that. All right, and then at the top, we'll put the COOH. At the bottom, the CH3. Okay, so if I'm drawing it like that, I'm basically viewing it from this side, because that's kind of the way these groups are wrapped around to the back. So if we just kind of twist that over and flatten it out, we would get this. All right, so now on each of these carbons, we have a dash and a wedge group. Okay, so if you're standing there looking at that, the OH and the CLs, those are the ones it's really hard to describe without a model, but if you're rotating that around like that, that OH and Cl, those are the ones that will come out towards you. Then the Br and the H will go back away from you. So just put those in. The OH out, the Cl out, the H, and the Br back. All right, now, honestly, it's perfectly valid to leave the structure like this. If you want it in more of the zigzag form, we can rotate around and put this methyl group like zigzagged onto the other side. Okay, by doing that 180-degree flip, that changes the directionality of these groups. So that brings the bromine to the front and the chlorine to the back. All right, again, if you build an actual model of this and then just actually rotate it around, you'll easily be able to see this structure, and then you can rotate that bottom carbon, move that methyl to the other side, and you'll easily see the 3D in that structure. Yeah?
Are you allowed to switch, like on the second one, can you switch where the hydrogen and the hydrogen are and the chlorine and the bromine?
Like,
Is that allowed?
like swap those two?
On the second one though, like can you switch which one's on the dash and which one's on the wedge?
No. No. So, and that holds true for any structure. Like you're never allowed just to switch two groups, because if you just say we switch these bottom two, that would end up being a diastereomer. If you switched these two and these two, you would have an enantiomer. So switching them all gives an enantiomer. Switching one or more but not all gives a diastereomer. Yeah?
If you have a meso achiral molecule in Fischer projection, can that have a diastereomer?
Yes. Yeah. I can show you one. In fact, a lot of people use Fischer projections to help them see like the meso structures. And a lot of that goes into like Fischer did a whole proof of the glucose structure using Fischer projections, but for example, if you had this structure, right, in the Fischer projection, it's actually pretty easy to see that you have this symmetry plane. Despite having these two chiral centers. All right, the one in the middle isn't a chiral center because this big chunk of a group on the bottom is the same as the big chunk of a group on the top. All right, so this would be an achiral meso compound. Okay, I could swap though, hypothetically, the H and the Cl on the middle carbon. Okay, those two are still chiral centers. And even in this structure, I still have this symmetry plane. And that means this is still considered an achiral mesocompound. Okay, but if you think about the relationship between these two, if I try to pick this one on the left up and set it down and superimpose it on the one on the right, well, the OHs will line up, but the H and the Cl won't. All right, so these two they're non-superimposable, they're not mirror images, these are diastereomers. Yeah?
And because of the symmetry, it would be impossible to make an enantiomer.
Correct. Yeah, so because it's achiral, all right, if you have an achiral molecule, it's impossible to have an enantiomer. And the reason for that is if you draw the mirror image, what may look like the enantiomer, it'll always be able to superimpose on the original. One other thing I'll point out is just that this carbon right here, where swapping the two groups gives you a stereoisomer, that's called a stereocenter. All right? Yeah.
Name compounds with multiple chiral centers, like assigning R and S.
Yeah, we can do that. All right, so let's just say we want to name this compound. So there's different ways you can go, or different orders you can go about how to do things. For me, I just like to identify the chiral centers first and go ahead and assign R and S. Okay. What will be helpful, though, is to draw in any implied hydrogens at the chiral centers. So do that. All right, now we have to prioritize our groups from 1 to 4. All right, at this first chiral center, the chlorine is 1. The hydrogen's 4. Okay, now you have to compare these two carbons. All right, so you start and you compare these two. Well, those two are both CH2s. They're equivalent. All right, so then move out and compare these two. Well, those are both CH2s. They're also equivalent. All right, so we still can't make a decision. So now let's compare these two. All right, this one is a CH3. This one's a carbon that has 2 other carbons attached. That is a higher priority. So we get 2 on the right and 3 on the left. All right, in this example, 4 is already back, so you don't have to manipulate that. Just draw a curved arrow from 1 to 2 to 3. That one's going around to the right. So that's an R configuration. All right, now we'll go to the other end and do the same thing. Figure out our priority groups. All right, well, the easiest one to pick out is the hydrogen. That's priority 4. All right, then we have this CH2, a CH2, and a CH3. All right, well, the CH2s are both tied. but the CH3 has a lower priority than either of those because it's just bonded to hydrogens. So we can at least go ahead and say this one's going to be priority 3. Now we still have these two to compare. All right, so let's move out one step further down the chain and compare these carbons. All right, we're comparing a CH2 versus a CH3. Well, this one is at least bonded to one carbon. This one's bonded only to hydrogens. So the one on the left will be priority 1. And that one's priority 2. Okay, so now, again, 4 is already to the back, so we don't have to change that. Draw an arrow from 1 to 2 to 3. This one's going around to the left, so that's an S configuration. All right, so let's redraw this so it's not such a mess. Okay, and I'll go ahead and put my R and my S down, so we have those. All right, as always, your first step is to identify the parent chain. All right, so if I put this on an exam, I could almost guarantee you that at least half go through and highlight this chain and think, oh, I can't count that wedge, so I just need to go on out here to make my parent chain. All right, that's not accurate. Just because it's on a wedge or a dash doesn't mean it can't be part of the parent. Okay, so let's try again. All right, now I can capture one extra carbon by highlighting into that ethyl group. All right, from there we need to number. And if I number from this carbon here, I run into my first substituent at 3 versus over here, my first substituent would be at 4. All right, so starting down here is better. So we go out to 9. So our parent will be nonane. All right, so to put our name together, I'm going to start with the stereochemistry designations. And I'm going to do them in numerical order. So I'm going to say 3S, 6R, all right, then just do your substituents as always. We have a C for chloro and M for methyl. So the chloro comes first. 6 chloro, 3 methyl, and the parent's nonane. Yes?
How do you know when to keep something constant when you're doing the numbering for the RMS configuration?
What do you mean by constant?
Because like in some of the videos you had, you said to like leave that alone and you drew a box on it.
Mm-hmm.
And then that.
Oh, I see what you're saying.
H to the.
Right. All right, so the question is, sometimes I rotated things around. How do you know when to do that? If your priority 4 group is to the back, like if you're doing an RNS assignment, you'll never have to do any rotations or manipulations because everything should be where you want them. But let's say you had, keep it a little simpler. If you were trying to do this one, and you prioritize your groups. Now, this is one where, honestly, I would just use the trick because 4 is out and go from 1 to 2 to 3. That looks like S, but since 4 is out, it's really R. But you could also manipulate this so that you actually get 4 to the back. Right? And in order to do that, what you want to do is find one group to hold constant, and basically it'll be any group other than the one you're trying to move and the one at the position where you want to get it. So basically I could hold this propyl or this ethyl constant. I'll hold the propyl constant since it's bigger. So kind of lock that in place. Then the other 3, it's totally valid to move those cyclically in a clockwise or counterclockwise direction. So to get hydrogen to the back, I can move that to the back, the chlorine into the plane, and this ethyl will come out to the front. So there's the propyl I held constant. I'm going to put the chlorine, like I said, into the plane. I moved the hydrogen to the back. And then this ethyl to the front, so I just need to add like one more carbon on there to have it to the front. Now you can just do the typical RS. 4 is now to the back. That's what we did. We moved it there. Draw your arrow from 1 to 2 to 3. That's going around to the right. So that's R. So it's something you can do, but it's not something you always have to do.
Whenever you're doing a ring, like a cyclic compound, do you have to hold 2 of them constant then?
That's actually a good question. If your chiral center is on a ring, you can never move it. Like you're just stuck. So let me just give you an example. Say you have this, well, that'll be all right. So for one, your hydrogen can never be in the plane because that's always part of the ring that's in the plane. So if it's to the back, you're fine. All you can really do with a ring is like flip it. Basically, let's say we take this carbon and flip that from the left to the right. So if we flip that over, okay, what that will do, by flipping it over, that puts the bromine back and brings the hydrogen out. So you can never rotate around the chiral center on a ring. Basically, if you build a model of like the one we just did versus this ring, on the model you can actually spin those 3 groups around. If you try to do it with the ring, you'll be stuck. You won't be able to move those groups. And if you switch those 2 groups, you would change the configuration of the chiral center. So you would have an enantiomer if you did that.
If we have to do the RNS for one of those, wouldn't it be better to use the one on the left than on the right because the hydrogen's already on the dash?
Yes. Yeah, so definitely. If I had thought this through, I would have drawn this one first and then flipped it over to get that one. But yeah, if you were doing the RNS, this first compound would be the one you would want to use. Yeah?
Could you do a degree of unsaturation problem where there's more than just carbon and hydrogen?
Yeah, so are you talking about just from like a structure?
Or just no?
So for the formulas, you can't do that yet. We're going to do that today in class because there's a special calculation for the formula. But you can do it from a structure. I'll just give you one here. Let's see if we can do this. A couple more things in there. So I'll show you like the two ways you want to be able to do it from an exam, for the exam. Let's say you're given any structure. Basically, you count a double bond is one unsaturation. A ring is one unsaturation. And I won't put this on an exam because I don't know if we've talked about it yet, but a triple bond has 2 pi bonds, so a triple bond is 2. All right, so then doesn't really matter what all's in your structure, just count up what you have. Here I have 2 rings. And I have 2 double bonds. So there's 4 degrees of unsaturation. Basically, that's telling you something with this number of carbons and other atoms. By getting rid of double bonds and rings, you could add 8 hydrogen into that to get a totally saturated formula. Yeah?
What about the other atoms? Didn't they take place of hydrogen?
They can, but just to kind of show you how this works. So basically, if a double bond takes the place of 2 hydrogen, because right now there's a hydrogen here and here. So if I let me add 2 hydrogen to that double bond, 2 hydrogen to that double bond to get a new molecule. All right, this is all hypothetical, not something you would actually do. So I added 2 extras there. Two extras there. All right, so that took care of those. But then, these rings each count as 2 unsaturations. So let's hypothetically say we break these rings apart. Well, where you break those bonds, you have to fill those in with some new bond. So you would need to add a hydrogen to each of those carbons. We had one there and there. There and there. So now, once you add all of those across, with this compound, with this number of carbons and all of these heteroatoms, it's impossible to add any more hydrogen to that and retain a valid structure. All right, so that's kind of the background for where these unsaturation numbers come from. But in terms of, what's the other part that's important for the exam, let's just say that I gave you C5H8 and asked for the number of unsaturations. All right, now we're going to learn today in class a little bit more formal way to do this. But essentially, you know how to figure out a saturated formula. You do CnH2n plus 2. So for 5 carbons, we have 5H2 times 5 plus 2. C5H12 would be the saturated formula. So then, in going from 8 hydrogen to 12 hydrogen, how many have you lost? You've lost 4 hydrogen, or gained, however you want to think about it. Okay. Every unsaturation is a 2 hydrogen loss. So, loss of 4 hydrogens is 2 unsaturations or 2 degrees of unsaturation.